Hi, this is Barrett Givens, and in this video, I want to talk about the extended Euclidean algorithm. So the extended Euclidean algorithm is something that you can do starting from the standard Euclidean algorithm, and then it allows you to sort of like do a little bit extra with your Euclidean algorithm. In this video, what I'm going to do is I'm going to demonstrate the extended Euclidean algorithm for one example. Then I'm going to develop a little bit of theory so that we can find a shortcut for the extended Euclidean algorithm. And then I'll finish by working another example, but using the shortcut that we've developed. Okay? So to start off, let's say that we want to look at the GCD of two numbers. Let's say we look at the GCD of the numbers 3024 and 1776. So using the standard Euclidean algorithm, you get what I can see on the left side of this screen. So I get 1776 goes into 3024 once, one is the quotient, and then plus 1248, 1248 is the remainder, and so on and so on. Next, you do 1776 divided by 1248. The quotient is 1, and the remainder is 528. Then you do the same thing with the numbers 1248 and 528 and so on. And what we find is that the GCD, it's the last non-zero remainder. So the GCD is 48. Okay, now to begin the extended Euclidean algorithm, what I'm going to do is I am going to, first of all, I'm going to name the two numbers I started with. I'll let A be the bigger number and B be the smaller number. And I do this really just to make the algebra and the steps and what's coming next a little bit cleaner, because otherwise you kind of end up feeling like you're drowning in numbers, okay? Now, the next thing I did was that I took each one of these equations on the left and I rewrote them by solving for the remainder. So for example, this one I solved for 1248 and I have somehow erased it. So let me fix that. 1248 is 3024 minus 1776 times 1. Okay, there, fixed. So I solved for 1248 by subtracting the 1776 to the other side. Then I took the 528 and I solved for 528 by subtracting the 1248 to the other side. I solved for 192 by subtracting 528 times 2. That's right here. Okay, and so on all the way down. And so these numbers down here on the left of this middle part, these numbers are the remainders in my normal Euclidean algorithm. Okay, now what I'm going to do is I'm going to write each one of these equations in terms of A and B. So for example, for the first one, I will write 1248 is 3024. Well, that's A. And then 1776, that's B. So this is plus negative B. Okay. And let me just highlight that because I'm going to want to come back to that equation in a second. All right, next, 528. What do I write instead of 1776? Well, looking up above, 1776 is B, so I'll write B there. And then I'll have minus 1, that's this 1 right here, times 1248. Well, 1248, that's the one I just highlighted. That's A plus negative B. So then I will solve this. I'll just simplify this, I should say. 528. How many A's do I have? When I distribute the minus 1, I get a negative A plus 2B. Okay, I will highlight that one as well. Next, 192. Well, 1248, I see above that 1248 is A plus negative B. And then minus 2, 528 is negative A plus 2B. I'll distribute that negative 2, combine the like terms, and I get 192 is A plus 2A, that makes 3A, plus negative B minus 4B, that's negative 5B. And I will highlight this one. Couple more. 144 is 528, looking above, that's negative A plus 2B, minus 2 times 192, that's 3A minus 5B. Distribute that -2, combine like terms, and I get 144 is negative a minus 6a, that's negative 7a, 2b plus 10b, that's 12b. And let's go ahead and save and highlight that one. And 48 is 3a minus 5b minus 1 times negative 7a plus 12b. So 48 is 3 plus 7, that's 10a, minus 5b minus 12b is minus 17b. Highlight this one. And last one, 0 is negative 7a plus 12b minus 3 times 10a minus 17b. And so 0 is negative 37a plus 12 plus 3 times 17. That's 12 plus 51, that's 63b. That is the last one that I will highlight. Okay. And so this is the extended Euclidean algorithm. All right, I'm going to pause for one moment. All right, I have plugged in my charger, so hopefully I can complete the video. All right, so this is the extended Euclidean algorithm. And the point of the extended Euclidean algorithm, what you see by following the extended Euclidean algorithm, is that every single one of the remainders can be written in the form of a linear combination of A and B, okay? And so in particular, for example, if I wanted to solve 3024x plus 1776 times y equals 48, I could look right here and say, well, 48 is 10a minus 17b. Well, a is 3024, so this is a times 10 plus b times negative 17 is 48. So what I've done here is I've solved this equation. I found an integer solution, x equals 10, y equals negative 17. So the extended Euclidean algorithm is typically used to solve equations that look like ax plus by is equal to the GCD of a and b. And we actually get a little bit more than that. We can see that every single one of the remainders in the steps of the Euclidean algorithm, every single one of these remainders can be written as something times a plus something times b. Okay, so this is the extended Euclidean algorithm. All right, so the way that students often see this in classes is that often what happens is maybe you're given something that looks like this. Solve this where x and y are integers. And so one solution can be obtained by doing the standard Euclidean algorithm, then solving for the remainders, writing it, substituting a and b. A is the bigger number and b is the smaller number, and then doing these sort of algebra steps, and then you will get your answer. All right, so that's great. So if you want to use the extended Euclidean algorithm this way, you can just always do it this way, and that's fine. If you don't want to see what I'm going to do next, that's okay too. But what I am going to do next is I'm going to talk a little bit about maybe we can find a shortcut because this was a lot of algebra. It's very prone to errors, okay? So let's see if we can find a shortcut. All right. Here are the formulas that I just found, but I just removed some of the noise, okay? I just simplified it down to just like the key formulas, the ones that I highlighted along the way. And then let's simplify this down even a little bit more. What I've done here is I've just taken the coefficients, and I'm not even sort of thinking about if they're positive or negative. So for example, here I have 3a minus 5b. I just wrote that down over here on the right as 3 and 5. Negative 7a plus 12b, I just wrote that down as 7 and 12. And so what I'm looking for is a shortcut where I could find these numbers in this column on the far right without having to do quite as much algebra. Is there a way that I could find these numbers more easily? Okay. So in the next little bit, what I'm going to do is I'm going to derive the formula. But it does get quite messy. If you want to skip ahead and just see it in action, you could do that at the end of the video and then come back if you want to see this, or maybe you want to see this right now so it doesn't feel like the formula just comes out of nowhere. Okay, so what we're going to do is we're going to get into some sort of sticky things with a lot of subscripts. Subscripts is the word I'm looking for. Okay, so what I have on the left here, this is the normal Euclidean algorithm. We take our two numbers, a and b, and we write a is b q1 plus r1. q1 is the quotient, r1 is the remainder. And then we repeat the process with b and r1. b is r1 times q2 plus r2. And then we repeat the process again with R1 and R2. We just keep taking the divisor from the previous step and the remainder, and then repeating the division algorithm over and over again. And then eventually you get 0 as a remainder. And whatever the remainder was right before that, that's your GCD. Okay, so that's what's on the left. Now in the middle, this is kind of what we were hoping for. We were hoping to have something that looked like R1 is a times x1 plus negative b times y1. And R2 is negative a x2 plus b times y2. Let me actually back up one bit because I did mean to say over here, I meant to label these. So I'm going to call these right here xi and yi. And I'm going to notice I left off the negative signs here. But one thing I want to notice is that the signs, the positive and negative signs, are sort of predictable in what's happening right here. It's always that, for example, let's look here at 1248. The A is positive and the B is negative, and then they switch. Then the A is negative and the B is positive, and then they switch again. So they alternate. It always goes from a positive something A minus something B to negative something A plus something B. So they sort of go back and forth. And so one way that I can write this right here is I could say that in general, if I look at plus or minus axi minus byi, that will give me the remainder ri. Okay, that's kind of what I'm labeling these variables xi and yi, and noticing that if I subtract those two, and then I might have to do a plus or minus, it'll alternate plus or minus, and I'll get ri. And I'm going to be a little sloppy with those. Okay, so the way I have it written here then is I have R1 is ax1 minus by1. And then R2 is negative ax2 plus by2. R3 is ax3 minus by3. So I'm flipping the minus sign back and forth. All right, now let's think about a particular example. So let's think about a particular example where we have three of these remainders in a row. R sub I minus 2, R sub I minus 1, and R sub I. Three of those remainders in a row. Those three remainders are related by this equation. Those three remainders would have come up in the standard Euclidean algorithm by this equation. So what I would like to do is take this equation right here, substitute in these three expressions for the three different remainders, and then see if that tells me anything about how the x's and y's relate to each other. So we're just going to do this very carefully, okay? So for ri minus 2, I will substitute in this expression in terms of a and b. So for ri minus 2, I will write axi minus 2 minus byi minus 2. That's my ri minus 2. Then I'm going to have my qi times ri minus 1. For ri minus 1, I'll substitute in this equation. Negative axi minus 1 plus byi minus 1. Okay. And then plus ri, I will get axi plus negative byi. Okay, now let us simplify by combining all the terms that have an a on each side and all the terms that have a b. So I will get a times xi minus 2 plus b times negative yi minus 2. That's on the left. On the right, I'll get a times xi minus qxi minus 1 plus b times negative yi plus qyi minus 1. Okay, let me just read over that and make sure I did that correctly. So I have, for the a's here, I have qi times xi. If I sort of distribute this q and then, write everything out long, and then after distributing the q, then I put the a terms together and I group them. So I would get xi times a right there, and then qi times xi minus 1, and that is subtracted because of that minus sign. And then b times negative yi, that's right here. And then if I distribute this qi over here, I get plus qi minus 1. Okay, so I claim then that the thing that's being multiplied by the a, that those should be equal, at least if they are equal, this would make this whole thing work. And then the thing being multiplied by the b should also be equal. And so what I get is that xi minus 2 is xi minus qxi minus 1. And negative yi minus 2 is negative yi plus qyi minus 1. And then let me solve that for xi and yi. So that system of equations becomes xi is q xi minus 1 plus xi minus 2. And yi is q yi minus 1 plus y I minus 2. All right. Now, it may not look like it yet, but this is the magical thing, okay? This is going to be the key to our shortcut. This is going to be the key to our shortcut. So these equations right here are going to be the equations that we use to make our shortcut. All right, let's see it a little bit more in action. I have a typo here. Let me fix my typo. Okay. So here is my table again. So in the table over here, I've added a little bit to my table. These values, for example, 3 and 5, those are the x and y values here. This column here is the column that I've added. Where did those numbers come from? 1, 1, 2, 2, 1, 3. Well, that comes from that in both of these formulas here, I have this qi being multiplied by an xi minus 1 and a yi minus 1. So those formulas, those numbers, 1, 1, 2, 2, 1, 3, those are these numbers. Those are the quotients on each step. So I make my table, and in my table, I put those values of the quotients that I get from the standard Euclidean algorithm, I put those there. And now what this equation down here, this equation in the box, the xi equals whatever and y equals whatever, what that is saying is that when I look over here on the right, on the far right, for example, how could I have gotten this 7 right here? This 7, it says that it's 2 times 3 plus 1. 2 times 3 plus 1. I take these three numbers to give me that 7. 2 times 3 plus 1. And then I take these three numbers, 2 times 5 plus 2. 2 times 5 plus 2. So multiply 2 times 5, add 2, that's 12. Same thing the next one. I do 1 times 7 plus 3. That gives me 10. 1 times 12 plus 5, that gives me 17. Okay? So these formulas, these recursive formulas, give us a blueprint for how to make a table of values. And we start the table of values, we always start with 1, 0, 0, 1. And that represents, the first line here, 1, 0, represents that A is A times 1 plus B times 0. And B is 0 times A plus 1 times B. One way I like to remember it is that this 1, 0, 0, 1 looks like the identity matrix. So that's what you always start with. And then each row in here you get by using these formulas. You multiply the value of Q, which is the quotients from the Euclidean algorithm, times the previous x, and then you add even one more previous x. That's what goes in this next spot. All right, I'm going to pause for 1 second, and then we're going to do an example. All right, we're going to do this example. Find a solution x and y in the integers for the equation 32x plus 41y equals 1. Okay, So 1 is the GCD of 32 and 41. I can realize that in a moment because I can notice that 41 is prime, so it doesn't have any factors other than 1 in itself. But to do the extended Euclidean algorithm, I have to start with the standard Euclidean algorithm. So even though I already can see that the GCD is 1, I have to use the Euclidean algorithm here. So I'll start with the Euclidean algorithm. 41, 32 goes into 41 one time with 9 left over. Then 32, 9 goes into 32 three times with 5 left over. Then 5 goes into 9 one time with 4 left over. And 4 goes into 5 one time with 1 left over. And then finally, 1 goes into 4 times with 0 left over. Okay? So these numbers inside parentheses, I try to be really consistent in how I write it. These numbers inside parentheses are always how many times the number goes into the other number, okay? Now, how many times does 9 go into 32? 3 times, because 9 times 3 is 27, and then 5 left over. So these are the remainders. Based on this, the GCD is the last non-zero remainder. So that's my GCD right there, okay? And then let's use the shortcut for the extended Euclidean algorithm. So the shortcut for the extended Euclidean algorithm, I'm going to make a long table. I will start up here with 1, 0, 0, 1, which I remember because it looks kind of like the identity matrix. And then on the left, what I'll do is I'll put my quotients. 1, 3, 1, 1, 4. Okay. And I like to put a little line right there. I'll show you why in a minute. Okay. Now I'm going to go ahead and just start filling in this table. And in each case, what I'll do is I'll take the number on the left. So the first one here is 1. I'll do 1 times the previous value, one row up, plus the 1 before it. So 1 times 0 plus 1. That's 1. Then I'll do 3 times 1 plus 0. That's 3. 1 times 3 plus 1. That's 4. 1 times 4 plus 3, 4 plus 3 is 7. 4 times 7 plus 4, 28 plus 4, that's 32. Okay, so each time I take the number on the left, I multiply it by the value 1 row above, and then I add the value 2 rows above. Let's do the same thing on the second column. I'll take this number, 1 times 1 plus 0. 1 times 1 plus 0 is 1. Then I'll do 3 times 1 plus 1, that's 4. 1 times 4 plus 1, that's 5. 1 times 5 plus 4, that's 9. 4 times 9 plus 5. 4 times 9, 36 plus 5 is 41. Okay, and each row of this extended Euclidean algorithm goes with one line of the standard Euclidean algorithm, okay? So, oh, hold on, let's also talk about the pluses and minuses. So I like to sort of annotate with pluses and minuses. So I remember that the first one always has the minus on the second column, and then I just alternate them the rest of the way down, okay? In this table, the way I do it, the left column is always for the bigger number, 41, and the right column is for the smaller number. And each row goes with each remainder. So this one is for the remainder 9, this one is for the remainder 5, this one is for the remainder 4, this one is for the remainder 1, and this one is for 0. So we're trying to find the solution to 32x plus 41y equals 1, which means we want to look at this column here where we get 1, okay? What this column tells me is it tells me that 1 is equal to -7 times a plus 9 times b. And you could check that with your calculator. You could put in for a, put in 32, and oh no, you know what? I have a mistake. No, I have it right. Okay. For A, I don't put in 32 for A. That was my mistake. What is A? A is the bigger number. A is 41. Okay. So I could check 7 negative 7 times A, which is 41, plus 9 times B, which is 32. I put it in my calculator, and I do get 1. Okay, I did it. Okay, and so what this tells me is that I can say, well, this negative 7 is the number that's being multiplied by 41, so y is negative 7, and x is positive 9. And that's my one solution. And so this is a shortcut method for the extended Euclidean algorithm where you do your standard Euclidean algorithm, you take your quotients, and you make a table. All right, let's do one more example, and I've done a little bit of a variation on this one. Let's use the extended Euclidean algorithm to find 121x minus 66y equals 11. And you should notice again that the GCD of 121 and 66, 11 goes into both of them. And if you think about it a little bit, I think you can convince yourself that 11 is the greatest common divisor. But again, we have to use the standard Euclidean algorithm to start the problem. So we'll just go ahead and do that anyway, even though we already know that the GCD is 11. All right, so standard Euclidean algorithm. 121 equals, how many times does 66 go into 121? I think it just goes in once and with 55 left over. And then 66, 55 goes into 66 once with 11 left over. And then 55 is 11 times 5. It goes in 5 times with 0 left over. And so I can see that the GCD is 11, which is what I thought. All right, now we'll make our table for our shortcut extended Euclidean algorithm. So in my table, I start with 1, 0, 0, 1, like the identity matrix. Then I put the numbers 1, 1, and 5 here. These are the numbers that I get from the quotients right there, 1, 1, and 5. And then I go down each column and I take my quotient times the x value from the previous row plus the x value from the row above that. So 1 times 0 plus 1 is 1. 1 times 1 plus 0 is 1. 5 times 1 plus 1 is 6. Okay, that's for that first column. Then I do it again for the second column. 1 times 1 plus 0 is 1. 1 times 1 plus 1 is 2. 5 times 2 plus 1 is 11. And then I'll annotate it with pluses and minuses. So I'll remember that the first one is always negative on the right, and then it kind of flip-flops. Okay. And then let me also just make a note here that this goes with A being the larger number, 121, and B being the smaller number, which is 66. So, and then let's also label these with my remainders. So this goes with remainder 55, this goes with remainder 11, and this goes with remainder 0. So we're looking for where it equals 11. So that means I'm going to use this second to last row here. So this tells me that 11 is negative A plus 2B. So that means 11 is negative 1 times 121 plus 2 times 66. And so looking at my equation up here, I have 11 is 121x minus 66y. So I have to look at that and sort of correlate what are the x and the y. Okay, what are x and y? So I see here that x should be negative 1. It might be tempting to say y is 2, but that's not quite right because of the minus sign there. So really, to get a minus up there, I would have to say y is negative 2. So I get x is negative 1 and y is negative 2. And I can check my answer. I can go back up to my original equation, 121x minus 66y, and I can try 121 times 1 negative minus 66 times 2 negative equals, and if you look, you'll see that I did get 11. Okay, so yay, it worked. There we go. Okay. All right, I clearly have to practice holding a calculator up to the camera. All right, so that was a pretty long video, I think. talking about the extended Euclidean algorithm. Let's just remember that we started by doing the Euclidean algorithm in sort of like its normal long format, and you can absolutely just do it this way to solve these sorts of equations. That's fine. After that, then we did some work kind of trying to figure out from all the formulas what the trick might be. And we got these two formulas down at the bottom that are circled. And based on those formulas, we came up with this method of making a table and then recursively finding the x's and then recursively finding the y's. And then we did this with two different examples. There was this example, 32x plus 41y equals 1, and we got one solution. And then we did another example, 121x minus 66y equals 11. So this tabular method, the shortcut, or the original longer method are both ways that you can solve things that look like ax plus by is equal to the greatest common divisor of x and y. All right, thank you for listening.